How's everybody doing today? Woo! Treefort. It's Saturday. I'm tired, but I'm also excited. Last day of Treefort, or last day of Hackfort. Thank you guys who have been showing up this whole week. I see a lot of familiar faces in the room. I really appreciate all the support this year. It's been a really fun one. I'm actually really excited about this talk. I'm not trying to make this guy nervous over here, but I was connected to Peter by a great friend and colleague, Ed Vasco at Boise State. We had a couple great conversations together. It's actually funny, Peter, you're like, oh, I used to be a musician. I was like, well, do you want to play Treefort? And he's like, oh, I don't know if I could do that. But then a month ago, you reached out and said, you know what? Maybe I'll bring my guitar. And I said, okay, well, I'll stop talking. But Peter, I'm super excited to have you out. And I hope you're enjoying Treefort.
Yeah.
And thank you guys. And we will have time for Q&A. I'll have someone in the room to help pass around a mic. But okay. I'll hand it over to you, Peter.
Cool. Thank you, Sean. Oh, hello. Thank you for attending. I appreciate it. There's like a lot more people than I expected, so this is very cool. My name is Peter Bordow. This is a little bit about me. I'll tell you a lot more here in a couple of minutes. I'm a distinguished engineer for Wells Fargo. I work in the cybersecurity line of business, and I work with emerging technologies. My main responsibility has been around quantum technology in the context of cybersecurity as well as fraud detection, quantum systems. So I've been tracking the whole quantum technology industry and inventing and training others and doing a lot of that stuff. And so I actually do a lot of these presentations. I travel around quite a bit, but usually when I travel to a conference and I present on the subject, everybody in the conference is from somewhere else, right? So it's never about the place that I'm going. It's always about the people that are attending. But here it's a lot different. So here I'm in Boise to talk to Boiseans, right? Is that what it is? Boiseans? Yeah. Okay. Okay, all right, that's good. So this is a lot more personal for me. So I really appreciate you showing up. And it's kind of crazy about how I got here. So yeah, this is not about how you got here, it's about how I got here. So as Sean said, a very old friend of mine, well, a longtime friend of mine, he's not quite that old, Ed Vasco runs he's actually the director of the Institute for Pervasive Cybersecurity, and they have a booth over in the main hall over here too. So go talk to those amazing folks. Anyway, Ed has known me for a very long time. He's been one of my most trusted friends, advisors, kind of like a big brother who's younger than I am, clearly more mature than I am. And so, yeah, Ed and I have known each other. We've worked on some pretty cool projects together. But he said, yeah, you got to talk to Sean and you got to come out to Boise and do this gig. And as Sean said, I originally was asked to do a music show and a technology show. Okay, and I'm going to tell you about my music stuff here in a second too. So here's the thing that's different. When I show up at a usual conference, right, I am representing Wells Fargo and I have to be a certain way. I have to say certain things. Not here. So Sean said, one of the things he said is when you come, bring all of yourself, right? Just bring who you are and, let it all hang out. So here we go. That's Ed Vasco. For those of you who don't know Ed, great guy. He's the reason I'm here with Sean. Really, it's an honor to be here. So here I am. I've come, all of me. This is a map of my schizophrenia. I was actually born and raised in New York. I now live in Arizona, outside the Phoenix Valley, in a tiny little town northeast of Scottsdale, which you've probably heard of. We have about 15,000 people in the town. And yeah, I've been there for about 35 years or so. I have been a recording and performing artist. I say have been because it's been like 15 years, maybe 20 years. So you guys are really going to be the acid test here. And I'm really into martial arts. In fact, it changed my life. So did obstacle course racing. I don't know if has anybody heard of the Spartan race or the Tough Mudder or, those sorts of things. So I started in 2014 and I weighed almost 300 pounds. And martial arts and obstacle course racing saved my life. And today I'm a second-degree black belt in Taekwondo, black belt in Hapkido, and a maniac for these courses. So I'm going to tell you about my technology, my music, and a little bit more about me. But first, a little bit more about me. So I have albinism. I am a person with albinism, okay? And so while I don't have pink eyes, I do have vastly affected eyes since birth. So I have what's called low vision. So it's very pixelated, like low resolution. Remember the old days when low-res TV was out there? Mine's a lot worse, okay? So y'all look the same to me, okay? I can't tell you apart. And I'm also what they call photophobic. So I have extreme sensitivity to light, which is why I wear sunglasses when I present. It's not just because I'm cool. And then I also have nystagmus, which is a condition that stems from these guys where my eyes move back and forth involuntarily since the day I was born to compensate for the dead spots on my retinas, which is kind of weird, you know, especially at a traffic stop when you're looking at the cop and, you know, all that. But what's really hard is that after a long day of about 2 hours of working, my eyes tend to get really tired and they stop moving back and forth, but my brain continues to compensate. So the world begins to move back and forth. So there are a number of challenges in all of that, but I get through it. Then, as I said, martial arts and Hapkido, Spartan racing. Oh, and this is important. So it's now official. 17 years in a row, voted best grandpa.
Hell yeah.
All right, so thank you. Arguably the most important distinction of all of this. Okay, so technology and music, there's the so much more. Okay, so a little bit of ancient history. 23 years ago, when online music was really early, there was a main website called mp3.com for unsigned artists, right? And so that was in the early days, Jurassic period of the internet. So I have 7 brothers and sisters, and they all are somewhat musically inclined. So I decided to do a little home recording, upload my stuff to mp3.com. And out of nowhere, man, I had hundreds of thousands of downloads, 600,000 actually. I actually had the #3 song in the world on mp3.com at the time. And so, yeah, I mean, I was ready to change careers. I was on a national tour. I won the Golden Music Award for Blues Artist of the Year, all set to go. And then in 2001, the end of 2001, I was diagnosed with cancer. And all of that went into a screeching halt, right? So the cancer's gone, and so has the music been too. And I've shifted towards my technology career. So now I'm planning my big time comeback, okay? So with that, I am gonna subject you people to a song, okay? It won't take long. I have a few of them, but I'll play one for you now. And then at the end, if there's time and nobody's, you know, walked out on me, maybe I'll play another one, okay? So bear with me, let me get into character, okay? Now again, I haven't played in front of people. My wife doesn't count, but I haven't played in front of people in, God, 15 years at least. So this is like really terrifying. So even if I suck, you have to applaud, okay? All right, yeah, there we go. That's what I'm talking about. Okay, let's see if we can do this. Okay, so this first song that I'm gonna play was one of the ones that went viral, and it's called Raw Meat Boogie. In fact, you can search Spotify for Raw Meat Boogie, and you'll see that song and a bunch of others. All right, so let's get into character here. All right, sound guy, this is where you're gonna make your money today, right? All right, so let's see. Oh God, I'm so scared. Okay, here we go. Hope this works out okay. Thank you.
Do you have to throw a panic at you now?
Not yours, everybody else. God, I'm so glad that's over. Okay. Holy crap. All right. And here you thought you were coming to a technology presentation. Okay, where's my little clicker doohickey? Oh, there it is. All right, let's get to the cool stuff now, right? Let me tell you a little bit about my other me. So as I said, I work at Wells Fargo. I'm what's called a distinguished engineer, which is essentially the top of the food pyramid. They think I know what I'm talking about, and after many years, they distinguished me mainly because of the gray hair. But now, one of the things that I do is I plan strategy, I solve problems, and I mentor and I teach younger engineers and mid-level and senior engineers on the latest and emerging technologies. I am also the special advisor to what's called the Quantum Technology Institute, which is an international organization designed to theorize and develop use cases around quantum technology in all different industries. I'm also the chair of the PQC, or Post-Quantum Cryptography Work Group, in a financial consortium called FSISAC, and I think it's spelled out here somewhere. Doesn't really matter. And so I'm also a pretty prolific inventor. I have 16 issued patents as of last week, with 40 more applications in, all in the area of quantum technology, a couple in digital identity and some in biometrics. And then I've also been inducted into the Wells Fargo Inventor Hall of Fame and blah, blah, blah. So everybody thinks I know what I'm talking about. So let's get that straight. Today we're going to talk about quantum technology. But before we talk about quantum technology, I think it's important that we get a little bit of a history lesson on how we got to where we are today. And I won't belabor this point, but let's start at the beginning with classical physics. So a couple of good friends of mine, Sir Isaac Newton and James Maxwell. So for a long time, for hundreds of years, the world relied upon what we call classical physics. This is essentially physics that we could measure, experiment, explain with all of the classical paradigms that we have in the world today. And it worked really well. In fact, NASA today and space agencies today still rely upon Newton's equations for gravity when they calculate space travel and orbital paths and things like that. That's how sophisticated classical physics actually can be. But then something really crazy happened around 1920, 1925, what I like to call the first quantum technology revolution. You had amazing thinkers like Albert Einstein and Niels Bohr. And from these guys, we began to get a much clearer picture of the world, sort of counterintuitive, but the world of the atom, the world of space-time, and all of the technologies that we enjoy today. That's where Einstein came up with the relationship between matter and energy. It's where we've got lasers and satellite communications and cell phones and integrated circuits and virtually all of the technology that we use moment to moment, day to day, we take for granted, all came out of that event in 1925. But something else came out of 1925, the world of quantum mechanics. So at the time when these guys were figuring out how the atom was actually constructed with a nucleus and electrons, that light was both a particle and a wave, and all of these crazy ideas, the world of the subatomic became apparent. And guys like Max Planck, and I'm sure you've heard of Heisenberg. Y'all are fans of Breaking Bad, right? Right? And Schrodinger, and we've all heard of Schrodinger's cat. So these guys began to explain a world that was really counterintuitive, the world of particles at the atomic and subatomic level. And they came up with these very, very strange behaviors and strange phenomena. And really it began to open up really a whole different level of physics and a whole different level of understanding of the world. But really, you couldn't really do anything with this crazy quantum phenomenon because the engineering skills just didn't progress fast enough to be able to do anything with this quantum technology until the last decade or two, when engineers have figured out how to harness some of the very strange behaviors of the quantum world into the new landscape of quantum technology. Let's talk a little bit about what that strange stuff is. So there's a couple of properties that are really important to understand. Now, we're not going to get into a physics conversation Can do that offline or over a beer later tonight if you want. But there's two things that you should understand because these are the fundamental principles of all of quantum technology. The first one is entanglement, or what Einstein called spooky action at a distance. He didn't like this. He didn't like the fact that things happened in the natural world that he couldn't explain. Well, the fact is that there are relationships among these subatomic particles called entanglement. So for example, if you generate two photons from a source, or if you take a laser beam and use a beam splitter, and those two photons go off in separate directions, and let's say that they are 1,000 light years apart, let's say different sides of the galaxy. If you measure one of those particles, instantaneously, the other particle will react in a correlated action. So if you measure one particle and it has an upspin, the other particle will have a downspin, and it doesn't matter how far apart they will seemingly communicate faster than the speed of light. Nobody really knows why, but it's been demonstrated over and over and over and over. And it's not just photons. The same behavior happens with electrons, atoms, and in some cases, larger molecules, right? So there's this fuzzy line now between the subatomic world and the strange behaviors and the atomic world, things that we can actually see, right? But this is a very important principle. It's very strange. The other one in quantum weirdness is called superposition. And this is where Schrödinger and Heisenberg did some of their best work. So the quantum world relies on something called uncertainty. That is to say that, and so I have a wonderful laser pointer here. Let me use this. So, here we go. So in the classical computing world, you have bits, right? Digital. You have a 1 or a 0, and there's nothing in between. And it's like flipping a light switch, right? Well, in the quantum world, it's more like a dimmer switch, actually. So you have states that could be a 0, could be a 1, but could be everything in between. And you don't know what the state or the condition of that particle is until you measure it. You can actually place these particles into superposition, uncertainty, and then when you measure them, there's a probability of it being a 1 or a 0 or somewhere in between. And so how this really translates to the physical world, we used to think that atoms had a simple nucleus and that these electrons spun around the nucleus, right? And they were just these little grains of sand or these little balls that would fly around, and they were very predictable in their orbits and so on, but that's actually not true. How it really works is that there's this tiny little nucleus in the center of an atom, and then there's what we call a cloud of probability. So nobody really knows where these electrons are or how they're behaving in the atomic orbits until they're actually measured. And so we have a whole new paradigm shift on what it means to actually look at the fundamental aspects of the universe. So we're not going to get into a whole lot more about these quantum phenomena, but let me tell you how we use them. Well, first, let's talk about, I haven't looked at these slides in a while. So first, let's talk about quantum technology. So we use these superposition and entanglement and other weird things like tunneling and coherence and other things like that. But it applies to a lot of different areas in technology. So clocks and timing devices. So now we have clocks in the laboratory that are 100 times more accurate than atomic clocks. Networks and communications, ultra secure communications, quantum computing, obviously, sensors. And in sensors, they take individual particles and they can measure nano changes in gravitational and electromagnetic fields. We've got quantum materials, so new drug development, new material development. In fact, there was an announcement recently that a team at, and I can't remember the university, has just developed the closest thing to room temperature superconductors that anyone's ever achieved before. Now, this is a long conversation, but needless to say, superconductors are at the heart of things like particle accelerators and batteries and fusion energy and all of these areas. So we're actually on the precipice of a world that we can't even imagine yet. And then, of course, machine learning. So quantum technology is very good at assisting with model training, AI model training. And we'll talk about that in just a second. Okay, so what's the quantum advantage? Well, there's two aspects to this. One of them is in this world of possibility. So I'm switching devices back and forth. So in this quantum world of fuzziness, right? We measure a particle and we can get a percentage of likelihood between it being an upspin or a 0 or downspin or a 1. And we use that probability over and over. So we measure over and over and over, kind of like flipping a coin. And if you flip a coin enough times, you'll end up with sort of this bell curve. And if you run enough operations, you'll get the most likely answer, the most probable answer over a series of evolutions, right? And so that's really at the heart of quantum computing. And how does this translate? Well, again, so in a digital computer, you have what they call a register or a line of ones and zeros, binary code, right? And every bit is unique and holds its one place in the numeric sequence. But in the quantum world, you can actually entangle these bits together. So every time you want to make a digital computer more powerful, you add one more bit and you add one more exponent number. So if you have 1 bit, you can measure 1 and 0. If you have 2 bits, you can measure 1 through 4. If you have 3 bits, you can measure 1 through 8, and then 1 through 16, and then 32, 64, and so on, right? Pretty logical, very predictable. But in the quantum world, when you add another qubit, you entangle another qubit, you don't just get 2 to the n, but you get 2 to the n squared. So there's an exponential increase in computing power with every qubit you add. So if you have 2 qubits, you can measure, say, 32 numbers. If you have 3 qubits, you can measure 32 squared. If you have 4 qubits, you can measure that squared, and so on. So you can see that there's sort of this geometric growth of computing power using quantum computers. I have not mastered the laser pointer, I'm sorry. Okay, and so you run these progressions and then you get these probability distributions. You feed it an equation, you run it over and over and over and over, and then eventually you get the most likely answer. And if you run it enough and you have stable enough qubits and you have enough of them and they're not interfered with, you can get enormously more computing power than you can with traditional computers. The thing is, though, that quantum computers are not good at everything. They're only good at this sort of very narrow slice of mathematics. They don't deal with a lot of variables very well, and they don't deal with a lot of data very well. There's no such thing as quantum RAM just yet. So they're very good for bite-sized chunks of mathematical formulas, right? And then you reassemble them and you sort of get your product after that. What's our next slide? Okay, so with this massive computing power also comes massive threats. And you've probably heard about this, but quantum computers are mathematically shown to be capable of breaking much of today's classical encryption. What we call asymmetric encryption or public key encryption or TLS or SSL. You know it by a lot of different names. Every time you do an online banking session, every time you do an Amazon transaction, anytime you send a secure email, right, you're using one of these asymmetric encryption methodologies. And quantum computers, we know, will be able to break that. We don't know exactly when, but it's somewhere in the neighborhood, most experts say, somewhere in the neighborhood of 5 to 10 years. It's coming. And what's even more scary is there's a thing that I preach a lot about at work that we call harvest now, decrypt later. And we know from intelligence briefings and other technical aspects that there are bad actor nations today capturing encrypted data en masse around the internet, knowing that they will be able to break that encryption one day. And it's not just this mass harvesting, right? There's metadata associated with what they're capturing. So source and destination, the size of the packets, the frequency of the packets, things like that can tell these bad guys what's probably higher value than other stuff. And so we know that that's coming as well. But they hired me at Wells Fargo to help deal with this, right? Let me tell you about what we're doing. Well, first, let me break down the problem a little bit. So we said public key cryptography, okay? So without getting into a lot of cybersecurity mumbo jumbo here, the reason that public key cryptography is at risk is because you have what's called a private key and a public key, right? And your private key stays with you. And when you communicate with another site, you share your public key, which is a derivative, right? And that public key is essentially 2 very large prime numbers multiplied together to give a much larger number. And that's the basis for the encryption. And it takes classical computers, many cases, thousands, hundreds of thousands of years to be able to guess those two prime numbers that make up that one product. But quantum computers can do that much, much faster. We'll talk about that in a second. There's another kind of fundamental cryptography called symmetric cryptography. And essentially what all this is just a very long random string of ones and zeros. It's not mathematically derived. There's no formulas that produce it. It's just randomness, entropy, if you will, right? And so, yeah, that seems like that should be far more secure, but really, there's a thing called Grover's algorithm. Grover's algorithm is an effective or an efficient search algorithm, and actually, we think, will allow quantum computers to be able to guess those 2,000-digit random numbers. Now, it hasn't been mathematically proven yet, but instinct tells us that it's probably on the horizon. Now, I've been doing this technology stuff for 35 years, and I've seen a lot of new technologies come and go. And I have to tell you, what we know about this scares me a lot. What we know that we don't know, like Grover's algorithm, right? That scares me even a little bit more. But what really scares me is what we don't know that we don't know, right? So today, classical computers have tens of thousands of algorithms that are production ready all over the world. All the way up to AI, right? Every bit of code has some measure of algorithmic construction to it, and there's maybe 100,000 algorithms, right? Maybe more. But in the quantum world, there's only about 20 or 30 that are production ready. And so we're just at this very, very early stage. We don't know what hasn't been invented yet. We don't know what people haven't thought of yet. In 5 years or 10 years or even 20 years, it's just inconceivable of what will actually be invented and developed. That's what keeps me up at night mostly. So, okay, so this is a good example. So here's public key encryption. As I said, oh good, the pointer works. We take two numbers, these are very, very small, but let's say that each one of these was, say, 300 digits long. And we multiply those together and we get a key. And that's our public key, and that's what we send, and it takes classical computers hundreds of thousands or millions of years to be able to factor that number into its prime constituents, right? Multiplying is easy, factoring is hard. And that's why quantum computers are such a threat, because they could run the simulation and effectively look at all possible solutions simultaneously. And if you run the simulation enough, you can get the most likely answer within minutes. And that's what's really terrifying. Okay, what's the next slide? Okay, good. So we are building a quantum safe world. So what are we doing about this? So one of the things that I do is I educate and I collaborate. I work with a lot of other financial firms, and I work with firms in other industries as well. And we work on mitigating strategies. We work on alternative methods of securing data and privacy. We identify potential targets, right? We scan the enterprise, and I assist other companies with scanning their enterprises, looking at where that risk is. Where are the attack vectors most likely to occur? And then we come up with solutions. We have three classes of solutions, essentially. So we have more complicated mathematical problems to base our encryption on. These are called post-quantum cryptographic algorithms. And it's the National Institute of Standards and Technology that's leading the way in testing and developing these algorithms. Now, they're still based on mathematics, but they're more complicated mathematics. And so, in my opinion, this is sort of a stopgap measure. Now, you can drop one algorithm in for another, and it's sort of a quick fix, but it's not going to solve the problem. The real solution to the problem are communications based on physics, not math. So one of the things that I work on is a system where we can exchange particles across a fiber optic cable, what we call Alice and Bob, A and B, right? And so Alice sends Bob an entangled particle. Bob measures that particle. And by measuring that particle, Alice knows what the correlated measurement on her side will be. From that, and it's done with a whole bunch of these particles, right? From that, these algorithms develop the key material. So in essence, Alice and Bob get to establish these cryptographic keys without ever exchanging any of the key material. There's another way to do this. It's a little bit less exotic, but when we transmit across that fiber optic cable, We now have very, very sensitive equipment that can measure the loss of photons over that fiber optic cable. So we know if somebody's eavesdropping. And we call that person Eve, right? So we have Alice and Bob and Eve. I know it's funny, but so we can actually establish and exchange key material, and we can know if Eve is listening on the line even before Eve captures any of the information. And we reset the session, we go to another side channel, or we do other things. And so we're working on these solutions that are physics-based. That's really the answer. That's actually one of the coolest things about my job. Where are we at? Okay. Okay, so we talked about quantum technology. We've talked about the threat that quantum computing brings. And we've talked about the mitigating strategy to protect your finances, your correspondence, your transactions. All of this is coming, okay? But what's the real promise of quantum technology? It's not just computing. So here are some industries that are going to see some radical, radical transformations. Everything from chemical and molecular science. So it's now possible to design materials using a quantum computer much more effectively than experimenting in an experimental lab of trying to conjure up these new materials. Same thing with drug development, right? Drug trials and drug design and mouse, what do they call these things where they use the mice and they inject them? Yeah, right? So that's all going to go away. They'll be able to model drugs using quantum computers so effectively and efficiently that they won't have to harm animals to do it. That's the day that I'm waiting for. Geology and meteorology, right? Quantum sensors can detect ultra-low vibrations. They can detect gravitational shifts. They can detect electromagnetic fluctuations. So things like navigation become pretty amazing. We can now navigate in deep space very, very accurately just by measuring the difference in inertia or gravity. We can also navigate around the world without the need for GPS. Secure communications, obviously, as we've been talking about. Machine learning, I mentioned. Supply chain and logistics, right? So worldwide shipping routes. Computers, quantum computers are very, very good at figuring out what's called the shortest path problem. So if a salesman has to visit 3 or 4 dozen places all over the map, quantum computer can quickly calculate the shortest route overall for that salesman to take. And that translates to more effective logistics, transportation, supply chain, and that's really going to be a profound impact. The brain-computer interface I want to call out for a second. So one of the things that I work with is virtual reality. We work with that in terms of learning and development and collaboration and training and things like that. So one day, these quantum sensors will be able to interactively create virtual realities for you. Unlike anything that you can imagine today, we'll be able to analyze brain patterns, things like control over prosthesis, right, for amputees, people who are paraplegic or quadriplegic, right, using just their thoughts, will be able to interface directly into the brain and the amazing breakthroughs that will come out of that. So there's a crazy world coming, and it's coming in the next decade or so. And you're going to see it little by little, and you're going to see the explosion eventually that will change everything that you know about technology. You'll see better medical imaging, like amazingly more resolution, high resolution MRIs, CAT scans, PET scans. You'll see material science breakthroughs, more efficient solar cells, which is a very important development. Smaller, lighter weight batteries, faster financial calculations. Yeah. I work for a bank and we're working on that too, right? Portfolio optimization, risk analysis, all of that good stuff. Not my gig. I work on the other stuff. More efficient aircraft and transportation routes, discovery of new drugs, AI and machine learning, more accurate weather forecasting. That's a big thing, right? Predicting snowstorms while it's sunny out and things like that. In fact, natural disasters can be predicted well in advance. even tornadoes, right? What tornado warning today is something like 12 minutes advance notice, best ever, something like that. Because we can't model the Earth's weather. It's far too complicated. There are tens of thousands of variables that affect weather in any specific geography, right? But with quantum computers, eventually, we'll be able to model that much more effectively. We'll be able to do those predictions. And as I said, more effective supply chain. And then, of course, better fraud and threat detection. It's another area I work on is detecting intruders electronically. So what we call intrusion detection systems. We can actually use some of the principles of quantum mechanics to be able to detect when somebody tries to break into a database or attempts to hack into a system. Of course, we're at Hackfort, so I probably shouldn't talk too much about that. Yeah, so it's about 3:40. So, oh yeah, and then the big thank you. It's really, really amazing to come here and share a lot about myself and all of that. And so I'm happy to take questions. I can play another song if everybody won't leave if I do that. But yeah, let's start with questions first, okay? Any questions? Yeah, and I'll start there because I can see your hand.
I'll bring over a mic.
Yeah, thanks.
How does the P versus NP figure into this?
You mean NP hard problems?
Yes.
Okay, yeah. So there's a class of mathematical problems that are identified as P or NP hard, right? And these are what we call intractable. So factoring really large numbers is one example of that, and there are a lot of them. And so yes, there are a whole class of mathematical problems that will be now solvable using the probability distributions and some of the other mechanics behind quantum computers.
Well, then who gets the $1 million? Who gets the $1 million then?
Yeah, well, I don't know. It's probably somebody who's got more than $1 million to actually build a machine to solve the problem, doesn't need the $1 million, right? It's a good question. Any other questions? I'm going to have a hard time seeing, so somebody help me field these.
In my experience, companies have seemed really slow to update their security, go from say like just even like MD5 to a more modern hash algorithm or something. So once quantum computing is here and they're actually able to crack those kind of things, and you'd want them to move on to whatever lattice-based cryptography or whatever. How do you convince these companies who kind of aren't even there now, like how in the future, how are you going to convince them to kind of keep up with things?
Yeah, that's a really good question. So yeah, it's a very big problem. And I've been working on that for a couple of years. And really it's a matter of messaging and communication, right? Really drawing home the impact of the risk to that company. Now I work in the financial sector, and I have to be honest that there's a lot of collaboration, a lot of cooperation. The executives and the CEOs of all of the major banks all understand this problem. And while I'm very lucky to be on the forefront in developing the technologies to mitigate these risks, we all understand what the problem is. And really the message is, we may not all be in the same boat, but we're all rising to the same tide. And this is everybody's problem. It's a little bit like Y2K, right? Because it's global, but there's no end date, right? There's no line in the sand. We don't know what date this is going to happen. And there's a lot of work to be done. And you mentioned the MD5 cryptographic transition, right? There are a lot of companies that would actually scare you that are still using MD5 or SHA-1, SHA-2, right? These cryptographic transitions take a very, very long time. And so most companies have already embarked on this journey, most large companies. Now, the smaller ones will wait, sort of following in the wake, right? And adopting the technologies and the solutions that the larger companies are developing. So it's a trickle-down effect, if you will. But I do a lot of speaking engagements. I talk to a lot of executives. I try to explain this problem in the terms that they can understand, like you'll lose your customers. Most people understand that, right? So yeah, but I don't mean to be flippant about it, but there's a lot of messaging and conversation going on, not just in finance, but in insurance industry and all of the industries, actually, in the medical field and all of those areas as well. So it's a journey. It is a journey. So they have people like me that stand out, I guess, to send the message. Any other questions?
Got another one over here.
Okay.
Thanks for speaking to us today. This has been really interesting.
one of the areas that I have been kind of obsessing over with respect to this topic that I didn't see in the array of like areas of disruption that you had in that one slide is like public policy. One thing, because I'm an attorney, and I've been thinking a lot lately about how quantum computing could potentially affect the way that we like measure social outcomes and sort of do social sciences and statistics, and how it is potentially kind of like a malicious tool for governments to kind of tinker with human behavior because they know in advance to a greater degree like social or political outcomes in different domains.
Wow.
Which I think is...
All right, how much time do we have?
Well, I was going to say, I find that really disconcerting, and that's why I wanted to ask if you have any, like, if anybody that you know talks about that, or if you have any kind of, like, recommended reading on that subject. I have a corollary question, which is, who is your favorite guitar player and why? Okay. But you can forget that if, in the interest of time, if necessary. Thanks
we'll start with that one, because I know the answer to that one. So my favorite guitar player is Johnny Winter, okay? I don't know if you guys know. You probably know his brother, Edgar Winter, okay? So he's an albino too. When I was growing up, when I was very young, the one thing that was true for me is that I was different and alone, right? From not being able to go outside in the sun to all of these, I don't want to get into it, but then there was Johnny, right? Who was an albino and played music that really moved me. So that's the answer to that. So, okay, on to the really tough question. So it's funny you mentioned that. Of course, it comes from a lawyer. So I'm actually going to Barcelona later this year to talk about the difference between the trajectory of predictable technology evolution versus self-fulfilling prophecies. So in other words, it's the ethics of quantum technology. Now we know about ethics of AI, right? You've probably heard Elon Musk talk about this quite a bit, right? Model training and bias introduction and things of that nature, right? But in quantum technology, you bring up a very good point. Theoretically, it has the capability to scan the internet, crawl the internet, look at all of the geopolitical parameters, governments, conflicts, things like that, and then make predictions about what might occur. Well, it hasn't happened yet, right? But it is theoretically possible. It's not even mathematically proven yet. But yeah, there's a group that I work with that talks about ethics in quantum computing and quantum technology. And it's something that's very much on our minds. In fact, it's the same group that does most of the technology development, scientific development work in this country. So Argonne National Labs and Lawrence Livermore and Brookhaven and other really big research facilities, we all talk about what the downfalls are, what are the risks from a geopolitical sense. So it's a very good question. And next year, if they bring me back, I'll give you an update. I promise. Okay.
All right. Got another one back here.
Yeah, so I've got two questions, and the first question's got a couple with it. So
we'll get a pen.
I'll streamline it.
All right. Yeah.
All right. So what's one thing that you're absolutely like personally passionate about, or something that you predict will just be mind-blowingly changing for the world? And then what industry do you think will be affected the most from this? I know that we have an attorney in the room, so he's probably figuring out what he's going to major in next, because that's probably going to eliminate it. And then the last question that I want you to answer is, what is something that terrifies you about this technology personally?
Wow, that's a lot of questions. All right, let's see if I can remember.
It's only three.
It's only three. Yeah, well, up here it sounds like a lot more. So what am I passionate about? Okay, so this is kind of funny, but kind of serious. All right, so I'm getting up there in years, right? And I have an Oculus. Oh, I shouldn't say a brand name. So I have a virtual reality headset, right? And I really enjoy it, although it's really primitive and it's, it is what it is, right? I envision a world where quantum sensors will interface directly with my brain, not intrusively, not like through surgery, but like surface mount apparatus that will be able to construct a real virtual world, right? Like anything that you can imagine with all the sensory input, right? At the end of the day, our brains are quantum computers. We work on entanglement and superposition, and our neurons function the same way a quantum computer does. And so it is theoretically possible to build an interface so that I can live in a magical reality with taste, touch, sight, smell, all of those things. So real you can't distinguish it from what we think is actually reality. That's a whole separate conversation. So I'm looking forward to that day, and it better be before I die. Like when I'm 90 and drooling on myself, that's where I'm gonna live, man. That's what I'm really passionate about. So what scares me? Well, the cryptographic implementations of quantum computing scare me. You know, I work for a really large bank, and we have millions of endpoints all over the world. And I have to secure, well, I don't, but people that work with me have to secure all of these endpoints, right? And I think that not just my bank, but banks in the United States, banks around the world, and then Amazon transactions, medical records, that's what really scares me. And I think we're working hard towards that. And what was the third question?
What industry do you think will be affected
The most. I think they're all going to be affected. I think first you'll see drug development and material science, because modeling complex systems is a little bit easier than it is to, say, factor a 4,000 digit number, okay? So you're going to see advances in that area. You're going to see better batteries. You're going to see more effective logistics and transportation routes. And then you're going to see better medical imaging. So I think those are the first areas that you're going to see, and that's my crystal ball.
All right. I think we have time for one more
question.
You had your hand up.
Yeah, so right now, most quantum computing systems are big, giant scale things that have to be built by like enterprises or colleges or something like that. But the logical question that this ends it with is, when can I build one in my house?
Wow. Okay, so I didn't really get into this, but that's a really good question. Okay, so today, the most popular or most well-known quantum computers are what we call chandeliers. They're these giant apparatuses, okay? And there's all of this engineering, and I should have had a picture of one. Next time I'll remember. But down at the bottom, in a tiny little silver cylinder, right, about this big, about that far around, there are the subatomic particles. And all of the other stuff, right, is all meant to isolate and prepare those particles for computation. They have to isolate temperature, almost absolute zero. They're called superconducting computers because they need superconductors to cool to a fraction above absolute zero. They're susceptible to electromagnetic interference, vibration, noise, temperature changes, all of these things. It's an engineering marvel that they've actually built these things, but they're not the only ones. So there are other modalities. There's a field called photonics, right? And so instead of using electrons or other particles, they can capture photons, and they can actually capture photons in silicon-based integrated circuits. So today we have quantum random number generators on chips. So they use essentially a variation of a laser to be able to generate photons and create these random numbers, and they can capture these photons and they can work on them. So you're going to see that field explode. Then there's ion capture, where they can cool a particle, an ion, if you will, with using lasers down to a very low temperature, and they can act on it in predictable mechanisms, right? And they can run these operations on it. There's NV centers. There's all kinds of competing technologies for quantum computers. And it's kind of an arms race right now. Advances in one modality spark advances in other modalities. So right now you can buy a 2-qubit system based on photonics. It's about $8,000, I think, the last time I checked. There's not much you can do with 2 qubits, but it's fun to learn how to program on. Mostly quantum computers will be cloud-based, right? You can access IBM's quantum experience today for free. You can learn how to program in quantum technology for free today. Google's machine, AWS machine. When will you have one in your house? Well, in about 20 years, they'll become mainstream. In 10 years, there'll be companion processors on every phone, right? There'll be quantum security chips in every phone in the world. That's the day I'm working towards. So it's coming. It is. Just be patient. Is that it?
Okay, that's it. Let's
All
give
right.
a round of applause for Peter Bordow.
Thank
everyone.
you very much.
Great
Really,
talk,
thank
Peter.
you guys for showing up. I appreciate it very much. Yeah. Everybody sit down. Stop.
So basically, you mentioned it earlier, but you didn't really talk about it, was the tech regarding space.
Yeah.
What can that look like later on? Will it affect rocket ships and spaceships and the rovers that went around and explored?
Yeah, so in a couple of ways. So first, navigation, right? Right now, it's really complicated and difficult to navigate, say, from Earth to Mars launch, right? Lots of classical Newtonian math is used to calculate the thrust and the angle of trajectory and all of these things. Well, quantum technology will make deep space navigation much, much easier. You'll be able to calculate your place in the cosmos based on your movement, right? And so there's a lot behind that. The other way is there are some of these quantum phenomenon that are now, the scientists now believe could lead to more effective and efficient propulsion systems. So the holy grail, right, is to be able to come up with gravitational fields, right? To be able to bend the space in front of you so that you can actually achieve closer to light speed than you could with, say, combustion fuels or liquid fuels or things like that. You're going to see in the next 20 to 30 years, maybe 30 to 40 years, all kinds of new propulsion systems, new navigation systems. So that's really going to be a major game changer. If I wasn't as old as I am, I'd be looking forward to it. But
okay, we already gave one round of applause for Peter Bordow. Let's give a round of applause for Preacher.
Thank you guys so much.
Thank you, Jesse, my older brother. Thank you guys so much. Peter, oh my God, that was so cool.
Thanks.